Hello everybody, my name is Barisha and we are going GPU versus a CPU or GPU going mano a mano with CPU. It's a real challenge, who is bigger, faster, more efficient and so on. So we will watch the same operation which is executing on the CPU and GPU. One is C++ program about adding two vectors or two arrays of the numbers, integer numbers, with 3072 elements, and also the same thing executed on a GPU or on CUDA cores in this case particular. And we will see who is faster for this number of elements in the array. So let's go first with the C++ program, which will be executed on one single core. For this case, we will take that in option. Like we can, because this is multiple core processor, we can execute it on more cores. But for case of this example, and to be more, let's say, visual and more comprehensive about what is happening and what is going on there, we will go with one single core, like classical program execution. So we will first go through the C++ program. We see standard include directives, include IO stream, include the vector. This is for the vector or array manipulation, and include chrono. This is for the measuring time, because we are trying to measure the time for which it will be executed, or this calculation will be executed. First, we're going, of course, with integer main, like in every good, fine, and nice C++ program. We define number of the elements. We taking in account or defining vectors, input vectors or arrays A and B, which will be filled with ones, and they will have these number of elements. So probably Copilot give this solution and this, let's say, not library, but heading, because it's easier to manipulate in this form. And here in this array it will be storage. This array will be storage of our results of adding of these two elements. In later cases we will go with maybe multiplying, and we will play and compare what is happening. So we see here how to start. It is start of measuring time. Don't take in account this. Don't take in account these comments, because I forgot to put them in English. But I explained this. I explained these definitions, and we see here that we have how to start. This is for the start of the measuring of the time. I mean, we defining the moment we start measuring our time, and we take a sample of the time in this variable. Then we go here defining, of course, there is a for loop, and it's a sequential sequences of and it's a loop of adding, and we going through the same sequence with the different elements for the 3072 elements, A and B, A's and B's, and we are putting them into the C elements or C's. Then when we finish that, we start, or better to say, stop measuring the time with this. This is some of the standard libraries of the C++, so no need to go very strict and with the definition on it. But it takes current time, or takes present sample of the time, start and stop here, or end, and we will calculate the past time for this. Now we have the duration. It's a new variable which takes in account Also, this is from this library Chrono. We take here end moment minus start moment, and we count nanoseconds. So if you want to go further, you can go and check what is the prospect of this library and what these methods are exactly doing. But you see, it takes samples of nanoseconds of this variable and turn it in nanoseconds. And then we have the duration of that looping of the adding of the numbers. And here we are writing down, or we are going on the cout first 100 elements of this C elements to check out is this job done correctly. And then we go into the another row, and we have here the duration. Put it here in nanoseconds, and also this is added just in case that we want to turn this into the microseconds. But yeah, we can go with execution of this program. This is common program, let's say one of the most basics examples, so no need to go into much philosophy down there. It's everything, let's say, clear, and we can go and execute. We calling the compiler, going G++, and we are going also, what is the name, C1 dot CPP. That's the name of our file from which we taking this let's say text to make it and compile it, to make program out of it. And we can go O and go C1 dot exe. Okay, now we have executive program, and let's try to execute it to check out is it done properly. We need to put there I think it now going like this. Yep. C1 dot exe to execute it. Yep, there you go. And we have 17,600 nanoseconds for the execution on one single core, or almost 1800 microseconds. So on the single core for small number of elements, in this case, it is going very, very fast, which is obvious. But let's see our brother CUDA core. What is going on there? We have same things, IO stream, we have vector, we have chrono for the measuring, but now we have CUDA runtime.h heading, which help us giving the commands to the GPU. And we have one kernel here for the adding of the. We are adding two arrays, or two vectors, but better to say arrays. We input this is defining the kernel or method or function which will be executed on the GPU. Remember, on the GPU. And we are putting here some pointers to those arrays which are input. And here is in this one will be given the result of that adding. And we have number of elements for both arrays. And we are defining here idx. It's a variable, but this sign, when we use this and this and this, and I will explain what are those. We actually, with this variable, giving the defining multiple, let's say, variables for the thread execution, which will be executed in parallel. So one thread is, let's say, like when we have in for loop, when we have one assignment to the I, here we have idx. But this execution will be not in sequence and in the loop on the one core. We are creating multiple threads which will be executed on the multiple CUDA cores. And here we define the basic, let's say, the basic element of the multi-threading is this variable. But then we can put, let's say, we can form block which consists of multiple threads, and we define how many threads are inside the block, and we have variable block because we can have multiple blocks. So this is, let's say, the basics, and this is the main point, and let's say main thing and main catch what is happening there. And for each of these, let's say, for each of these defined parallel, not to say variables, but for multiple indexes which will be executed in parallel, but not in like we did it in classical way in a for loop. We will add these two elements for these one thread. This will be executed in one thread, and that will be assigned to the variable C, which we also put it here to store the results there. And then this is the defining of the kernel, which is planned to be executed inside the GPU. And now we have integer main. We defining the number of the elements. We define the size or type, this type size t, or some, let's say, value, which is 3072 times the size of integer, because we are making the we will later make the we will make and define the space for these two arrays in the memory. And we are doing this, we saw this also in previous case with the C++. We defining and making a new storage for these vectors. And they will filled with ones. Let's say beginning A and B arrays will be filled with ones, and there will be 3072 ones in both input arrays or vectors or whatever. We are here defining space and assigning the values on the CPU or system memory. And also for the result array, we defining the space, but which is of course not filled yet. And then we are defining that same thing inside the space of memory of GPU. We are putting here some pointers or defining some pointers to which will be assigned some memory or allocated. It will be allocated some memory on the GPU or graphic card. So these functions which are new and in front of them, you can see they are part of the CUDA package. We see that we are assigning the space a size of 3072 times size of integer. We are reserving the space, allocating the space for these begin and initial arrays, where we'll be move this from CPU to GPU memory, and then we defining the space for the result array, and this will be pointed to the this DC pointer, which are we defined here, and this method is actually moving from this space from the CPU to the GPU memory, and we are moving the not moving but take this copy from the this array and put it inside the memory allocated to the GPU memory. And you can clearly see which is this what is described here. CUDA mem copy. We are mem copying the memory from host to device, and also that's for the A, and that's for the B. From the copy of this array from the CPU memory or system memories, pardon, we are copying this to the GPU memory, which is allocated to the pointer D of B. And it's also, you must put here this that in the description, because there is another way around to go with this, but we will see that later. So we put it from the CPU to the GPU memory. We are starting now this measuring time, which we saw previously. Then we are defining number of number of threads which are inside the block, and this will be variable which will be put it on the function calling or kernel calling inside inside main program. And also here we defining defining number of the blocks. Here is the number of the threads per block, but we have now blocks per grid, or total number of the blocks, which are consist of 256 threads. And this is the standard way how to do it. Out of 3072, we divided this with 256, and then we on that case we, let's say, defining the number of the blocks. We are defining blocks because we have multiple elements inside the GPU on which we can execute actually this in parallel, so we don't making the queue for the execution of the adding just on one section of the GPU, because GPU have multiple, let's say, architectural elements which we call the streaming multiprocessors. Inside them there is 128 CUDA cores each. So usually there is two that streaming multiprocessor in one TPC, and let's say one block is executing on the one TPC or two streaming multiprocessors, but we will check that out later. And we are calling the kernel here, which is called add arrays. with the number of the blocks and threads per block. This is the input arrays. This is the result. This is pointer for the resulting array, and of course number of the elements for each of them. This will be executed according to this definition, and then we have auto start standard chrono blah blah blah. We are stopping the memory clock. We're taking present time, and auto and yes, we have the duration like in previous case, and we have writing the number of elements which are inside, and first 100 of them will be write it down, and then we have executed time written down here, time of execution, and we are freeing these allocated memories. So for this case we need to use VSL or Windows Subsystem Linux, because CUDA compiling needs that for the execution, and compiling of the program is dependent on must be on the Linux, some kind of Linux system. So let's not go too much further with this. It's called with let's compile it nvcc. This is for the calling of the program of the compiler. Then we have CUDA 1 .cu. So then we have just a second. Then we have the /o. Then we have I think cc bin. I think that we have some here. GPU. Do we need this one? I don't know. Let's go further. Yeah, let's go like this. Or. I think. I think this one is cool. Okay. No. Okay, this will last a little bit longer, but we will. Just a second. Okay, we have this CUDA 1. We have also this CUDA 1 as an executable program, and we are doing CC bin, I think a CC bin using probably G++. Okay, let's try this. Okay, it seems that we have done it, and then let's now check it. Is it correctly done? Execution. We type here CUDA 1. I hope it will go fine. Okay, it's fine, but the execution time is much bigger than previous one, which is 2,400,808 nanoseconds, which is much bigger than 17,000 or 18,000 nanoseconds in previous case, but this is for the 3072 elements. We will increase the number of the elements and check the outcome of that, but I think for this case it is clear that we are now still faster with the C++ than with the CUDA program. Or CPU for small number of elements, 3072, is faster than the GPU in this case. But let's not stop there. We will see what is happening with the increase of the number of the elements for the arrays.